Hi everyone, today we are going to learn about how to simulate a control valve in Simulink. If you have seen the previous tutorial, in that tutorial I talked about shut-off valves. And by shut-off valves, I mean in those kinds of valves, we are only interested in the 100% open or 100% closed position. They are either fully closed or fully open, and we are not interested in simulating them somewhere in the middle, like half open or 60% open. But in another type of valves, which are sometimes called control valves or regulating valves or balancing valves, these valves are used to control some level or some flow rate or some pressure drop. And we are mainly interested in their half open position. So these kinds of valves have a characteristic curve or some characteristic parameter, which is called a flow coefficient. And flow coefficient is the pressure drop coefficient of this valve. And it is a function of the percentage of valve opening. So when the valve opens further and further, you expect the pressure drop to decrease. And when you close the valve, the pressure drop increases. So for any of these control valves, we have a characteristic curve which sets the flow coefficient against the stroke opening. So first, let me define the flow coefficient. Flow coefficient is the ratio of the flow rate over the square root of pressure drop. And it is the flow rate for which the valve is going to exert 1 psi of pressure drop. So here in this formula, Q is the flow rate in GPM, in gallons per minute, and delta P is the pressure drop in PSI. So it is in imperial units. There is an equivalent form of flow coefficient in SI units, which is the flow through the valve in cubic meters per hour, which is going to exert 1 bar of pressure drop. That is the SI equivalent of flow coefficient. But in this video, I'm going to stick to imperial units. So as long as the flow is in GPM and delta P is in PSI, this formula gives the flow coefficient. And you can see that for different types of valves, if you open the valve, like here, 100% means 100% open, the flow coefficient is going to increase. It means that it takes a bigger flow rate to exert the same amount of pressure drop. And there are thousands of characteristic curves out there, and today we are not going to talk about how to select one of them. We are only interested in simulating one already chosen valve. So suppose I chose this one, and I want to talk about what this curve is going to tell us. And the first point I want to mention is this operating range. And it says that it is advisable to use this valve only in 25% up until 75% open situation. So if you don't want to get the near fully open or near fully closed positions, you are only interested in somewhere in the middle. And there is a star here at 50%, and it is the sweet spot of the valve. So in order to choose the best valve suitable for your operation, you got to find a valve with the flow coefficient which is closest to the desired value at 50% open. So some manufacturers develop these kinds of graphs. Most of them do this, but also some of them develop these charts. And at these tables, you can see that the valve is 5%, 10%, 20%, all the way up until 100% open. And these numbers are the flow coefficients corresponding to each of these open percentage of the stroke. And here I have the flow characteristic values of thousands of valves, and I'm going to choose one of them randomly, and we are going to simulate it in MATLAB. So suppose I choose this one. Okay, here it is. So the valve is 5 all the way up until 100% open. And I'm going to copy these values, and in MATLAB I will define a variable named %open, and I enter these values. Okay. Then I will enter the corresponding flow coefficient. So CV is equal to all these numbers. Now I plot %open versus CV. And this is going to be the characteristic plot of this valve. It is CV against the percentage of the valve opening. So to simulate it, I open Simulink, and it is going to be an isothermal liquid model, but it is the same for thermal liquid. So here under isothermal liquid, I find valves and orifices. And there are two options. One of them is the two-way directional valve, and the other one is an isothermal liquid orifice. So you can use either one of them. There is no difference. You see the settings are basically the same, and the calculations, they're all the same. So just choose one of them and stay with it. I choose the two-way directional valve, and I double click on it. In the previous tutorial, when I talked about shut-off valves, we just set the orifice parameterization in the linear area versus spool travel, because in that video we were not interested in the pressure drop in the half open positions. But today, in order to simulate the flow characteristic curve of the valve and the flow coefficients completely, I'm going to choose the second option, which is the area versus spool travel. So area is the open area of the valve, and the spool travel is showing how much it is open or whether it is closed. And you may instinctively think the third option is better to use, since it asks for the volumetric flow rate and pressure drop. But in my experience, it is not advisable to use this one, since it asks for a pressure drop vector. And you gotta find a vector for pressure drops, and it is going to interpolate and extrapolate it linearly. But we know that the pressure drop is most of the time consisted of some constant value multiplied by the square root of the flow rate. But if you select this option, it asks for the pressure drop vector and interpolates and extrapolates it linearly, while we know that the relationship between the pressure drop and the flow rate is quadratic. So I will choose the second option. Now the question is how to relate the orifice area vector to the flow coefficient. Okay, so I opened the MATLAB documentation for this block. And if you have seen my previous tutorial, there I talked about how this valve is going to calculate the pressure drop or the flow rate through it. And we came across this formula, and there I said that as long as the area of the port is set to infinity, this whole denominator term is going to be equal to 1, and it is going to make the calculations so easier. And it is interesting to know that this value is by default set to infinity. So I'm going to ignore this term, and what remains is that m dot is equal to some constant values times the square root of the pressure drop. And here I have this equation. And just to make the calculations easier, I will set the constant CD equal to 1. So if it is equal to 1, then what remains is this formula. And since it is mass flow rate, and I am interested in the volumetric flow rate in the CV formula, I will put the density times the volumetric flow rate instead, and we will have this form. And I will put the density to the other side of the equation, and it is going to be somewhere in the denominator. So it is what remains. And since MATLAB asks for the area of the orifice, I'm going to keep it in the one side of the equation and all other terms to the other side. So by rearranging the formula, here is what we get. The area of the orifice is equal to the volumetric flow rate over the square root of pressure drop times the square root of half of density. And if you look closely at this formula, you see that Q over the square root of delta P is equal to CV. If you remember this formula, now this term has appeared in the area formula. But right now, I cannot simply put CV instead of these terms. And the reason behind it is that we must use a consistent set of units. As I defined CV, Q was in GPM and delta P was in PSI. And since there is some difference in the units, I cannot use CV directly in this formula. And for this formula to be consistent, here I write this formula in its units. So as long as the volumetric flow rate is in cubic inches per second, and the area is in inches squared, and the density is in pound mass per cubic inches, and delta P is in pound mass per inches times squared seconds, this has consisted of some consistent set of units. But now to be able to use the flow coefficient in this formula, there are three questions to be asked. The first one is, what is the density of water in pound mass per cubic inches? The second question is, how to convert GPM into cubic inches per second? And the third question is, how to convert PSI into pound mass per inches times squared seconds. And now I'm going to answer each three of these questions. And I want to show you how easy it is to find the answer to these questions. For example, I Google water density in pound mass per inches cube. And I don't even have to open the links. It says it is 0.036 pound per inches cube. So this is the answer to the first question. The second one was, what is the conversion rate to convert GPM into cubic inches per second? And there are lots of links, and if you open any of them, it says 1 GPM is equal to 3.85 cubic inches per second. And the third one is a little more difficult to answer since it asks for an unusual pressure unit. But I asked Google to convert pressure from PSI to pound mass per inches times squared second. And I found one link that has these units. So 1 PSI, here it is. I found PSI in this website, calculan.com. PSI is pound force per inches squared. And I converted to pound per inch time squared seconds. And this is the conversion factor, 386.0.88. So now I have the answer to all the three of my questions. Here is the density of water in pound mass per inches cube. Here is the conversion rate of GPM into inches cube per second. And here is conversion rate of PSI into pound mass over inches times squared seconds. And although I already have the answer to all the three questions, I want to explain the third one a little bit more. So just to show that you do not have to always memorize things, and look at it like a quick tip about how to find the conversion factors for yourself. So PSI is by definition pound force per inches squared. And what we know about pound force is that it is equal to 32.174 pound mass times foot over squared second. It is a definition of pound force. Okay, so, and I have to add 1 over inches squared at the end of this unit. And there only remains one problem, and it is that in the numerator we have feet and in the denominator we have inches. So to convert feet into inches, I have to multiply it by 12. So 1 foot is 12 inches. So 32.174 times 12 is the conversion rate or the conversion factor to go from psi into pound mass over inches time squared seconds. And this multiplication gives the same result as 386.088. You can check it for yourself just to make sure. Now I go back to the original formula, which I had right here. And now that I have the conversion factors, I can put the flow rate in GPM and multiply it by the conversion factor. And the same goes for the pressure drop, where I can use PSI if I add the correct conversion factors. And I put the density in pound mass per cubic inches. So now that Q and delta P are in my desired units, I can put CV instead of Q over square root of delta P. And I have all the conversion factors, and you can calculate these constants manually, and you will come up with this formula. The area of orifice is equal to this constant times the flow coefficient. Now I go back to MATLAB and I'm going to start entering numbers. So here is the valve I wanted to model, and it said that the stroke is 0.75 inches. So I set the spool position at the full open or the maximum open orifice area 0.75 inches. Then it asks for the spool travel vector, and that is exactly this percent open vector, which is going to be pasted right here. But since these values are in percentages, they have to be divided by 100. And then it has to be multiplied by 0.75, since these are percentages of this value. For example, we want the valve stroke to be at 0.75 position when it is 100% open. So 100 over 100 times 0.75 is going to give us that value. I'll change the unit to inches, and for the orifice area vector, I will copy this value, I will paste it, and multiply it by this constant that I found, 0.0263. It is in inches squared. And remember that I defined the discharge, I assume that the discharge coefficient is set to 1. And by default, the port areas is set to infinity. Infinity is infinity, so you do not need to change the units, but just to keep it consistent, I will set it to infinity of inches squared. So now the valve is completely modeled, and it's time to check if it works all right. So I'm going to add 2 reservoirs. Then I add an ideal pump. Which is going to transmit the desired flow rate. I set it to a constant volumetric flow rate in GPM. And also I want to see the pressure drop across this valve. So I had a PS Simulink converter, and I asked for the pressure drop in PSI units. I also need a display block. And by the way, I have already made a tutorial on the sensors in Simulink. So if you want to learn how to work with pressure sensors or temperature sensors or flow rate sensors, make sure you watch the tutorial. So now that I want to check if I have modeled this valve correctly, I suppose that it is at 40% open position. And by definition, it says that if the valve is at 40% open position, then its flow coefficient is 6.8, meaning that if the flow rate is equal to 6.8 GPM, then the pressure drop has to be equal to 1 psi. So that is what I'm going to test right now. I set the flow rate to 6.8 GPM and I set the signal by a PS constant block. So I want it to be 40% open. So it is 40% of 0.75. It is 40% of the 100% open spool position, which was set to 0.75. And the unit has to be in inches. It is so important to change that. Now I want to run the model, but I know that MATLAB is going to show me an error, so I have to be careful. First, I add solver configuration block, and under the utilities, I add the flow properties. But yet again, I will come across an error, and it is going to say that the first element of a spool travel must be 0. So what this error basically says is that MATLAB has to know the opened area of the valve when it is 100% closed. Although it may seem like a contradiction, but as I completely explained in the previous tutorial, when the valve is fully closed, there has to be some leakage area. MATLAB, for some numerical reasons, does not accept the valve to be fully closed, and if I set the area equal to 0, it is going to show me an error. So here's what I typed here. I add a 0 position to this vector, and I also added a 0 number to the area vector. So right now it says that when the stroke is 0, it is fully closed, then the area is equal to 0, and it is so tightly closed that there is actually no leakage area. But if I run the model right now, it is going to display an error. It says the elements of orifice area vector must be greater than 0. So the MATLAB forces us to always accept some amount of leakage. And that's why you have to enter some small value, some negligible amount of leakage through your valves, which is not a bad assumption for control valves, since control valves cannot be shut completely and fully and tightly with no leakage. They usually have some leakage. And I'm going to add 1 in -10 as the area of the valve when it is fully closed. So now I want to run the model. And this is the value which is so satisfying. It is almost equal to 1 psi. And it is the pressure drop of this valve when it is at 40% open position, and 6.8 GPM of flow transmits through it. And if I double the flow rate, I expect the pressure drop to be multiplied by 4, since the relationship between the pressure drop and the flow rate is quadratic. You see, here it is. Okay, here the simulation is already complete, but I just want to add a few tips and maybe we can play around with this model a little. The first thing I want to mention is that if you are transmitting a fluid other than water, or maybe you're transmitting water at high temperatures, the effect of the change in density has to be seen in the definition of the flow coefficients. So I hope you are familiar with the definition of a specific gravity, which is the density of the fluid over some reference density, which is most of the time taken as the density of water at 4 degrees Celsius or at 39 degrees Fahrenheit. And in our simulation, I used water. It was the default option. But if you want to change your liquid, make sure you do not forget to add the specific gravity in your definition of the flow coefficient. And the next thing I want to do is play around with my model a little. So imagine I have my high pressure source at 2 psi's and low pressure one at 1 psi. And here I need no pump, and instead I add a flow rate sensor. I add a volumetric flow rate sensor, which is going to display the flow rate in GPM. And since the differential pressure across the valve is going to be equal to 1 psi, I do not need this pressure sensor anymore. And instead of a constant opening for the valve, I add a PS ramp. And initially, it is going to set the valve at fully closed position. And after 10 seconds, it is going to open the valve completely. So at the initial output, it is 0 inches. And the valve opening is going to increase at 0.75 over 10 inches per second. So after 10 seconds, the valve is going to reach the 0.75 spool position. So it is going to be fully open. I also add a scope block to see how the flow rate changes. And you probably might guess that this scope is going to be displaying the flow coefficient of the valve in a graph similar to this plot. So I'm going to define CV again. CV is the flow rate which is going to exert 1 psi of pressure drop. And in this model, the pressure drop is set to constantly 1 psi. And when the valve is going from fully closed to fully open position, the flow rate is going to change accordingly. And now I see the scope, and it is somehow similarly looking to this plot. Yeah. So now we have plotted the characteristic curve of a valve via Simulink, and it tells us that our simulation is all right and complete. And that concludes the lecture. Thank you for watching. Please let me know what you think about this tutorial in the comments, and make sure you follow and subscribe my channel. Bye bye.